Welcome everyone to this Monash Cybersecurity Seminar. Today we are happy to welcome Yang Yu, who is an assistant researcher at BNRS, Tsinghua University, and he got his PhD at Tsinghua under the supervision of Professor Xiu Wang in 2018. And then he did some postdoc works at CWI in the Netherlands and University of Rennes in France. And he is interested in lattice-based cryptography, and in particular making them practically efficient. And today he will talk to us something related to that. So he will introduce us to BAT, which is a small and fast KEM over and through lattices. Thank you, Yang. The scene is yours.
Can you see the slides?
Yep.
Okay. And thanks for your introduction, and thanks for your kind invitation. And I'm happy to attend the Monash Cybersecurity Seminar to communicate with you. And today I will present our recent work about KEM. This is a joint work with Piana Fook, Paul Kirchner, and Thomas Perlin. And in this work, I will present a new entry-based KEM called BAT. BAT achieves a good practical performance. On the one hand, it achieves the smallest communication size among all current lattice KEMs, and on the other hand, it has faster encapsulation and decapsulation comparable to the NIST finalist Kyber, despite the relatively slow key generation. Furthermore, another interesting point of BAT is that BAT may be seen as a KEM remit of NIST signature finalist Falcon. Both Falcon and BAT use optimal N2 trapdoor as their secret keys, but from an implementation aspect, BAT is much simpler than Falcon. It does not use complicated Gaussian sampling, and it can be fully implemented over integers. Okay, let's start with some background. Most of today's public key crypto systems, including RSA, ECC, would be vulnerable to quantum attacks. So to prepare for cybersecurity in quantum times, we need post-quantum crypto systems. So to this end, in 2016, NIST launched a project to standardizing post-quantum cryptography. Their scope includes post-quantum KEM, public key encryption, and digital signatures. And according to different hardness assumptions, there are several main families in the post-quantum cryptography. There are lattice-based cryptography, code-based cryptography, and multivariate cryptography, isogeny-based cryptography, and symmetric cipher-based and hash-based signatures. And among all these post-quantum crypto systems, lattice schemes actually are very strong contenders. Lattice schemes are dominant in the NIST post-quantum cryptography competitions. There are 3 out of 4 NIST encryption finalists, and 2 out of 3 signature finalists are lattice schemes. Lattice schemes, especially when they use an algebraic structure, have good overall performance. Lattice schemes are usually much faster than RSA and ECC crypto systems, and their parameter size are practically moderate. But the size of lattice crypto system is still much larger than that of RSA, ECC, and isogeny based schemes. When it comes to real-world deployment, the size of a crypto system really matters, and sometimes even more greatly than the speed does. For example, if a site has a large if a scheme has a large size, that would require extra packets and then which would increase the latency and the risk of packet loss in TLAs. Also, large sizes would increase the transmission energies, and which may be crucial issues for some low power embedded use case. Furthermore, large sizes would make the schemes not compatible with some constrained devices. So a question is, how small can a lattice scheme be? And to answer these questions, a natural option could be NTRU. These three cryptographers are the inventors of NTRU. And NTRU is one of the oldest lattice crypto systems, but it is still practical till now. And NTRU is also one of the encryption finalists and in the list competition. NTRU is parameterized by the underlying ring R and a global modulus Q. In this work, we restrict the rings to power of 2 cyclotomic rings. And one distinguishing feature of NTRU is its key pair structures. The secret key of NTRU is essentially a pair of short polynomials, Fg, in the rings. And its public key is the ratio of these 2 short polynomials modulo Q. And such a special NTRU structure allows to reduce the data to 1 ring element, and which can provide NTRU with very good compactness. Indeed, in the NIST computation, the NTRU KEMs is not highly compatible. It's not highly comparable to LWE-based schemes, but that is mainly because of their conservative parameter selections due to some security consideration. And for signature, the NTRU-based hash and size signature FACN is indeed the most compact signature schemes among all NIST signature candidates. The underlying lattice of NTRU crypto systems is called NTRU lattice. It is defined by the public key H and the global modulus Q, and it is a rank 2 modulus over R. There are 2 common NTRU key structures in use. The first one is called the vector type. In this setting, the NTRU secret key is one single short vector Fg of the NTRU lattices, and the other one is called the basis type, or sometimes I call trapdoor type. And in this setting, the secret key is actually extended to a short basis of the NTRU lattices, in which there are 4 short polynomials. And these 2 different NTRU key structures have different applications. The vector typed NTRU secret key have been used in both public key encryption, like the NIST NTRU KEM, and the Fiersheimer signature, like the famous Bliss signature schemes. And in this setting, the norm of secret key Fg is about square root of n times a small constant number c. And currently, the trapdoor type NTRU secret key is only used in hash and size signatures, including the original NTRU size scheme, and its provably secure variant proposed by Stanley Stanfield, and unpractical instantiations FACN. And in the practical instantiations, the norm of small f small g is set about 1.17 square root of q, and which was shown to minimize the Gram-Schmidt norm of the NTRU trapdoor basis. And this allows to achieve the best quality of signature. In this work, our focus is NTRU-based KEM. So let's first recall the classical untrue encryption. There are three public parameters of classical untrue: the ring, the global modulus Q, and a small masking modulus P. P is usually chosen as 2 or 3 or a small polynomials in the rings. And the key pair of classical untrue encryption follows the vector type. And to encrypt message M's, the ciphertext C equals P times H times R plus M, where R is a short randomness. And to decrypt the ciphertext C, one first compute F times C modulo Q as C prime, and then compute C prime modulo P and multiply the inverse of secret F modulo P's. And the correct decryption is ensured by the condition the polynomial P times PGR plus FM, the coefficient of PGR plus FM are bounded by the half of Q. And this condition actually ensures that the intermediate ciphertext C primes equals PGR plus FM and without modulus Q. So this is equation over integer without instead of over DQ. So one can recover the message M by the second and the third steps. And if we take a closer look at the masking modulus, and we can find the masking modulus P is actually has an adverse effect on both the size and the security. In fact, if we fix the size of secret key FG and the size of randomness R and M, the introduction of masking modulo P would increase the size of the global modulus Q. And such a larger modulus Q then implies the lower security if the size of secret key and the dimension of the lattice is fixed. However, the masking modulus P seems necessary to the decryption of classical untrue encryption because it requires such a masking modulus to clean out the terms PGR in the intermediate ciphertext C primes. So a natural question is it possible to remove the masking modulus, and how much we can gain if the decryption if the decryption does not require the masking modulus. And to solve these problems, and we propose a new untrue decoding algorithms based on a new untrue decoders. Our goal is to recover the message M from the ciphertext C. C equals HR plus M, and there is no masking modulus during the encryption. And our main idea is to replace the previous vector type untrue secret key with untrue trapdoor. And compared with the one single short untrue vector FG, the untrue trapdoor can provide one more equation for decryption. That is, we can use F to build one equation and use big F to build another equation. And this allows us to solve two unknowns, the randomness R and the message M, by solving these two linear equations. And this idea was actually used in the earliest lattice crypto system, GGH. And we can see the ciphertext C actually corresponds to a point close to the untrue lattices. And the distance is the size of M and the randomness R. So the decryption is essentially boils down to CVP decoding. And there are two efficient CVP decoding algorithm proposed by Babai. The first one is Babai's round-off algorithm, and the second one is nearest plane algorithm. In the context of NTRU, the round-off algorithm performs as like this. And since the basis B is NTRU basis, so it is almost free to compute its inverse. So in the NTRU context, the round-off algorithm is convenient. And the correctness condition of round-off algorithms is related to two intermediate polynomials. The first one is fm plus gr, and the second one is big F m plus big gr. So in this sense, the small f small g and big F big G behaves almost the same. Is treated almost the same. And for the nearest plane algorithm, the decoding is more complicated. It requires to use Gram-Schmidt orthogonalization of the NTRU trapdoor, BF star, and the Gram-Schmidt basis of NTRU trapdoor has special structures, and the correctness condition of nearest plane NTRU decoding is also related to two polynomials. The first one is the same, fm plus gr, and in the second one, the big F big G is replaced by its Gram-Schmidt vector F star G stars. And these two decoding algorithms has their own advantage and disadvantage. First, the round-off algorithms is simple and fast, as we mentioned before, but its decoding ability is weak. Here, the decoding ability means how large MR can be decoded correctly, and we hope the algorithm can decode large M and R. That means large noise means higher security. But in round-off algorithms, the size of big F and big G is usually much larger than the size of small f and small g. That means the size of MR is mainly depending on the size of big F and big G. And compared to round-off algorithm, the nearest plane algorithms has a strong decode ability, because the size of Gram-Schmidt norms is significantly reduced compared to the original big F big G. But the drawback of nearest plane decoding is it requires expensive pre-computation to compute the Gram-Schmidt orthogonalization, and also it requires high precision arithmetic to deal with Gram-Schmidt orthogonalizations. So we want to achieve a better balance among the decoding ability and simplicity and efficiency. So to do so, we propose a new NTRU decoder based on the original round-off algorithm. To improve the decode ability, we propose to replace the big F big G with its Gram-Schmidt vector F star G star, and we use optimal NTRU trapdoor as infectant to make the size of F star G star is close to the size of small f and small g. And to avoid the high precision arithmetic, we further replace the Gram-Schmidt vector F star G star with its integral approximation. And a trick here is that instead of directly run the F star G star, we propose to use approximate Gram-Schmidt coefficient B, and then compute the approximate Gram-Schmidt vector F prime G primes. And this allows us to get a good approximation of the Gram-Schmidt vector also allows us to have a convenient inverse of the Gram-Schmidt basis when we decoding and when we decode. And furthermore, we propose to refine the decoding. We also take into account the distinct distribution of the randomness R and the message aims, and we introduce a scaling factor gamma, that is the ratio between the standard deviation of M coefficient and the R coefficients. And instead of consider the size of F prime G prime, we consider the size of gamma F prime and gamma G primes. And also we consider the impact of the non-zero means of the coefficient R and M, because M sometimes is the expectation of M's coefficients is not usually zero. And putting all this together, we get our entry decoder. And the first 3 steps can be performed in the pre-computation, and the remaining steps only requires some basic polynomial additions and multiplications. And the correctness of our entry decoders is also related to 2 intermediate polynomials. The first one is the same, related to GS plus FE, and the second one is the approximate Gram-Schmidt vector. But the Gram-Schmidt is taking the scaling factor into account. And to analyze the decoding failure rate, we only need to bound the size of the GD, FD, and this boils down to bound the size of G abort, F abort. And here we can see the vector G abort, F abort is similar to the Gram-Schmidt vector of the big F, big G, but the intermediate polynomial V is not the Gram-Schmidt coefficient. In this, the scaling factor is before the big F bar. And to estimate the size of G abort, F abort, we propose a heuristic estimate. And its size can be expressed by the canonical embedding of F and G due to the untrue structures. And we heuristically model F C, F bar C, G C, G bar C as independent chi-square variable. And by some routing computation, and we have the size of F abort, G abort should be close to this term. And particularly, when the scaling factor gamma equals 1, and our heuristic estimate is also applicable to the case of vacuum trapdoor. But our heuristic estimate suggests that the optimal of standard deviation of F should be fourth root of 2 times square root of Q over 2n's. That is slightly larger than the previous value 1.17 times the square root of Q over 2n's. And we found the previous heuristic argument of vacuum seems problematic because their argument is based on projection heuristic, and they ignored the simplicity of the entry basis. The simplicity of entry basis means once the first half of Gram-Schmidt norm of the entry basis are determined, then the remaining Gram-Schmidt norms are fixed as well. And with our heuristic estimates of the norm of G abort and F abort, and we can arrive at an upper bound of our of the decoding failure rate of our N2 decoders, and we verified the values experimentally, and our experimental results are even smaller than our heuristic estimates. And in practical schemes, to minimize the decoding failure, we suggested to choose some sigma F, such that sigma 1 to be close to sigma 2. Okay, let's move to our scheme BAT. BAT stands for Basis with Attractive Trapdoor, and this is what written in the paper. But we give this name mainly to indicate BAT as a remit of Falcon signature. And the BAT shares the same leading design principle with Falcon, that is minimizing the overall communication sizes. And so to this end, we apply two orthogonal techniques. First, we use optimal N2 trapdoor along with our new N2 decoder, and also we use deterministic rounding error to replace the random noise for further ciphertext compression. And the BAT is built over a power of 2 cyclotomic rings, and its modulus Q is of the form bk plus 1, where k is the size of ciphertext coefficient. And also, we introduce parameter q primes to control the approximation precisions for the approximate Gram-Schmidt basis. And this is the key generation algorithm of BAT. And at a high level idea, this algorithm is very close to the key generation of Falcon. It first sample a short N2 vector Fg, and then complete the N2 trapdoor basis by solving the N2 equations, and reject the N2 trapdoor if the quality of the N2 basis is not sufficiently good. But unlike the key generation of Falcon, we don't need to compute the complicated Falcon tree, and the secret key of N2 is only contains the N2 trapdoor BFG and intermediate vector W. That is the approximate Gram-Schmidt coefficient. Indeed, the key generation of BAT is expensive. It is much slower than the key generation of N2 encryption, but it is still at least 10 times faster than the key generation of RSA. The main bottleneck of key generation is solving N2 equations. That is given small f small g and found a shorter vector big F big G satisfying this equation. And this is done by polling press the algorithm as in Falcon. But compared with the Falcon implementations, there are several improvements on the solving N2 equation on the step of solving equation in BAT. First, BAT has much smaller parameters, which leads to better performance and significant RAM savings in solving N2 equation. And also, we implement the key generations without using any floating point operations. That means BAT is completely FPU free, And this is the encapsulation algorithm of BAT. And the ciphertext actually consists of two parts. The first C1 and C2. C1 is actually a ring LWR, a ciphertext of randomness ACE. And the C2 is the hashed randomness ACE XOR the intermediate message M. And this actually corresponds to the what's the case average case correctness transform. And we can see our encapsulation is highly simple and faster. The main computation is only one polynomial multiplication. And the computation of C2 actually corresponds to the worst case to average case correctness transform that was proposed in a resident work about NTRU. And this transform allows to make the decryption failure rate independent of the certain message. And also, with this transform, we can prove the underlying encryption is IND-CPA secure. But this transform would introduce an additional number bits overhead on the ciphertext. And the decapsulation algorithms essentially our new NTRU decoders. So it is also efficient. The main computation consists of a few polynomial addition and multiplications. And BAT tolerates a small decryption failure, and to lower the impact of decryption failure, we suggest to use some well-bounded randomness SE, and this makes the actual decryption failure even much smaller than our previous heuristic estimate. And we propose two parameter sites for 128 and 256 bits of security. And for better performance, we set the modulus Q as some small entity modulus. This allows BAT achieve a very fast multiplication. Furthermore, we suggest a parameter set particularly for lightweight use case, in which the degree of the ring is only 256, and the modulus Q is only about 128. And this and the lightweight BAT do not use entity modulus because there are suitable entity modulus of the suitable size. And this is the performance benchmarking among BAT and other KEMs. Here we can see, compared with some famous Lattices KEMs, BAT enjoying very good size. Its size is significantly smaller than others. And the size of BAT is actually very close to the size of RSA 4096. And BAT also has, and while the key generation of BAT is relatively slow, but the frequent key usage, that is the encapsulation and decapsulation of BAT, is quite practically efficient. We can see, compared with the NTRU, compared with the NIST finalist Kyber, the encapsulation speed of BAT is about 3 times of Kyber. But the decapsulation is two times slower than Kyber. So we think the frequent key usage of BAT is sufficiently efficient. Now, I would like to give a simple listic explanation of why BAT can achieve such a compact parameters. And as we know, the parameter condition of lattice schemes is heavily related to the correctness conditions if we assume there are some decryption failure. And we compare BAT with NTRU encryption and ring LWE encryption. For NTRU encryption, the correctness conditions is related to this polynomial PGS plus FE, and the correct decryption requires all the coefficients of these polynomials are bounded by half of Q. And when it where FG corresponds to the NTRU secret key, and SE corresponds to the randomness introduced during the encryption. And when it comes to ring LWE encryption, and the related polynomials becomes this one, where E0, E1, E2 are the randomness introduced during encryption, and FG corresponds to the LWE secret and noise, and the correctness conditions is require, and the correct decryption require all the coefficient of these polynomials bounded by Q over 4, not half of Q. But for BAT, the related polynomials is GS plus FE, and the upper bound is half of Q as NTRU. And if we suppose all the encryption randomness SE are of the same size, denoted by sigma E, and all the secret FG are of the same size, determined by sigma F. And we also suppose these three encryption algorithms has the same decryption failure that is usually determined by a tail-bound parameter tau. Then the parameter restriction can be summarized in this table. And we can see if given the same n tau sigma E sigma F, BAT allows the smallest modulus Qs among these three schemes, and the smallest Q implies the highest security. This means BAT can use the smallest parameter and achieves the highest security. Okay, let's conclude. In this work, we present a new NTRU-based KEM called BAT. BAT has a nice performance. It is more compact than all known lattice KEMs, and its encapsulation and decapsulation is faster, comparable to NIST KEM's finalist Kyber. And the complexity of the code as well as the running time is asymmetric. And the cheap daily operations of BAT make it favorable to small device. And its expensive key generations can be compensated by frequent key usage or regular key refreshing for forward sequencing. And BAT can be seen as a KEM remit of the NIST signature finalist Falcon. Both Falcon and Kyber use similar key structures, but compared with Falcon, BAT has simpler and faster daily operations. Also, BAT is implemented fully over integers and of even smaller parameters. This makes BAT more compatible with small devices than Falcon does. At last, I would like to mention some future work. Indeed, BAT is still in its infancy, and further research are required. And at first, we require further cryptanalysis for BAT, because in the paper we only consider some general methodology for concrete security estimate. But I think it could be interesting to investigate the impact of decryption failure, weak key, and small rounded error on the concrete security level of BAT. And also, I think the algorithm of BAT may be further optimized. For example, currently we use a simple average case to worst case correctness transform, but this would introduce some overhead on the ciphertext, and I guess maybe it is possible to replace this transform with a better one, and or we can simplify the encryptions with a nice security proof. Also, it is an open problem to accelerate the key generation. That is meaning about the accelerate solving the NTRU equation. At the last, there are also many work to do regarding implementations. We need optimize the implementation for small microcontroller, and also currently we are studying the side channel protection of BAT. And furthermore, I think it could be interesting to evaluate BAT maybe along with some NTRU-based signature on TLAs. And this is my talk. Thanks.
Thank you very much, Ying, for your very interesting talk. Now I'll ask if anyone has any questions. I may actually start while the others are thinking. Could you go to slide 29? 29? Yeah.
Okay.
Yeah, here it seemed to me like the difference between NTRU and BAT, if we take P to be 2, is about 1 bit, right? In terms of the size of Q?
The size of Q, yeah.
Yeah, so the size of Q differs by 1 bit approximately, right?
Yes, yes, the size of, because if we reduce the modulus Q by 1 bit, and then the security would increase.
Yeah, yeah, that's right. But I'm wondering how come the effect is like that significant? Because the ciphertext size was getting close to almost half of what NTRU achieves.
Because first the NTRU structure actually is more compact than ring LWE schemes, and also we use
I'm comparing
LWR.
NTRU to BAT. Yeah.
Yeah.
Yeah. So if you compare BAT to NTRU, I'm wondering how the saving in the ciphertext size. I think there are like more things than just the restriction on Q, I guess. Because just 1 bit saving in Q, I feel like it wouldn't give that much reduction in ciphertext size.
And yes, and actually the current NTRU proposal use somewhat conservative parameters to avoid the decryption failure. And I think it can be further compressed if we allow some decryption failure.
I see. For example, if NTRU didn't, I mean, if you didn't still use your new NTRU decoder, but you applied your other techniques to NTRU, can you reduce the ciphertext size?
I think if we only change the parameter of classical NTRU, and it is hard to achieve such a compact scheme. Because here, if we set, for example, if we set the p equals 2, and and this term would become square root of 5, and here is square root of 2. Yeah. So the modulo of untrue should at least larger than the modulo for bad.
Yeah. Stephen, did you have a question?
To find my unmute button. Thank you for the talk. I don't think we actually met each other before, but we are co-authors on a paper, so it's nice to meet you.
Yes. Hello. Hi, Professor.
Can you go back to the encryption or encapsulation algorithm? I have some questions about. Yeah. Oh.
Yeah. Encryption.
Yeah. So in line 3. It looks like there's some kind of rounding going on. You're kind of compressing C1 by doing rounding.
Yes.
And then because of that, then line 4 is kind of the error from rounding, and then line 5 you need some bound on the error.
Yeah.
So I'm just curious about how all the conditions work, because it seems unlikely that a uniform error will satisfy that bound. I guess this is a question about the size of K.
The size of K?
Yeah. Yeah. So how is K related to Q? Is it like square root Q or something?
No. K is much smaller than Q.
Okay.
You can see here K is only 2 or 4.
Okay.
K is very small.
So this is also only saving, well, again, it's a bit like what Mohammed was asking. It's saving one bit or another bit.
Yes.
One of the bits. Okay.
Any other questions?
But still, you need the error to be quite less than square root of n or something, right? Which, I mean, it seems to me the error is kind of uniform between minus q over k and q over 2k.
Yes. We assume the error behaves uniformly, but it is actually LWR error, so we need further analysis.
And so the encapsulation may have to run. It may fail, and you have to run it multiple times to get a right, because you have this restart in line 6. So in your examples, how many times do you have to repeat?
Sorry. Actually, I'm not being in charge of the implementation, but this bound is quite relaxed. I think we don't need to restart so many times.
Thank you.
Thanks.
Any other? Yeah, Rob, go ahead.
Yeah, thank you, Yang, for the nice talk. Sorry about my croaky voice. I have a cold. Yeah, I was wondering in encapsulation. So why don't you set the key to be the hash of S?
Yes, that is what I said in the last slide, because I think that it can be simplified to remove the C2 and directly treat S as the message M. But in the previous version, we didn't work out a security proof for this case. Yes, and if we replace S by M, and then we can only get a one-way CPA secure scheme encryption, right? It is not ND CPA. and also the decryption failure is dependent of the certain message aims. So we don't know how to apply the current FO transformation on this setting. But I think that could be done with some better security proof technique.
Yeah. Okay. Yeah. The other question was about because you said that you are only using integer arithmetic, right?
Yes.
So how did you implement all these divisions that you have in keygen, for example, all this rational? You use fixed point arithmetic, or?
Actually, I'm not very familiar with the implementation. This was conducted by Thomas Pauling, but as I know, Thomas used some FFT techniques with fixed point operation, and the main possible computation for is compute the Gram-Schmidt coefficient is this step,
Yes.
right? And it is and this is done by some. I remember it is used some approximate FFT fixed point. Yes, this is only. Yes, this is the only complicated step.
And do you know what is the precision needed, or?
The precision, you mean Q prime?
Yeah, I mean, for this computation of the Gram-Schmidt, what size of kind of integers do you use?
This Q prime, the Q prime is about maybe 10,000. It is median. Q prime is 16,000. It is median.
Okay. Yeah. All right. Yeah. Thank you.
Thanks.
And probably I have one last, or probably one question. Can you bring up the table of comparison, because I fully understood this at first, but then you mentioned that these are probably compared with different parameters. Like, for example, the decryption error is different. Are these having all the same security parameter? Because you quite achieved half the sizes of NTRU, right?
Yes.
And it's at the same NIST level 1 or NIST level 5, and but only probably you relax the requirement for the decryption error failure, right? Failure error in the BAT compared to NTRU, because you mentioned that NTRU has been conservative, but here you haven't been that much. Is that the case?
So sorry, could you repeat?
Yeah, my main concern here is that so what's the decryption failure error of BAT that you considered, and how is it compared to NTRU then?
NTRU does not have decryption failure. So
yeah, but I think one instantiation of them have the decryption failure, right? It's not NTRU, but it's the version that Ron mentioned, right? They have it.
Yeah. I guess maybe you mean the NTRU,
yes,
right?
Yes.
Yeah, in NTRU, the decryption failure is super low. It is very low. It is much lower than this.
Okay.
Yeah. So you
so
can see the
in
size of
NTRU
is
200.
Is large.
Yeah. Okay, I see. That's why you get like very large ciphertext and public keys.
Yes.
As well. Okay. I see. but for NTRU, that version of the NTRU, it's almost the same, right? Because NTRU basically it doesn't use any it doesn't have any decryption error failure, right?
Yes.
Yeah. Okay, but it still it achieves half of it, right? Okay.
Thanks.
Okay. Yeah, thank you.
Maybe I can ask one more question. So in the decoder, didn't you need two polynomials to run your new decoder? But the ciphertext seems to have just one polynomial. And then this C2, but yeah, I'm just ignoring C2.
Sorry, could you repeat?
So for your new NTRU decoder,
Yeah.
Didn't you need two polynomials to decode, or maybe I misunderstood that part?
Yes. Yes. In our embed, we do need two different polynomials for decoder. You can see. We need. This is actually we need to solve the linear equations. We need to solve both E and A's from the linear equations. So we need the two polynomials.
But both C prime and C double prime, they are derived from C1 in the actual bit encryption. So in the decoder, you have C prime and C double prime, right?
Yes.
But in the encryption, you just have C1. And you derive C prime and C double prime in decryption from C1,
No.
is that correct?
Here the C prime and the C prime is not the C1 in the encryption, actually.
But you do need to derive something similar to the C prime and C double prime, right?
Here the C prime and C double prime correspond to the intermediate ciphertext, like this. Is correspond to this term.
Okay.
Yeah.
Okay.
Yeah. But C1 in the encryption corresponds to this term, C.
Yeah. Okay. Yeah. So they are derived from C1. Okay. Okay. I guess any last question from you? Okay. Seems not. Yeah. Thank you very much, Yang. This was very interesting, and thank you everyone for tuning in. And hope to see everyone in the next seminar. Bye, everyone.
Thank you.
Yeah, great. Thank you. Very nice. Bye-bye.
Thank you. Bye-bye.